Hi Physics 2 class, welcome back. This will be our first information video. We obviously have to return back to refraction. Hopefully you guys haven't forgotten too much of this content as we get moving forth into a little bit more complex stuff as this unit continues to proceed. Well, it is a balmy 62 degrees in here. I actually wore shorts up here and a t-shirt and walked in to videotape this lesson. I guess they forgot to turn on the heat in this building. So I am freezing to death, so I'm going to make this thing really fast, or as quick as I can make it here. Most of these videos will stay under 15 minutes. As we move forward, we may have some that are a little bit lengthier, but I will try to keep them as short as possible and in smaller bites so that you guys don't get too bored with them. Alright, so on handout 6.21, which I put this on Canvas so that you guys can negotiate it. But on the back of the handout, there are a couple of prisms that are located. So, one thing it is not stated on here. Oh, yes, it is. Okay, on B it says that they are equilateral triangles. So I will keep these pretty easy on you. So once again, if you can't remember from your geometry days, equilateral triangles just means that all the interior angles are 60. All right, so let's get started with our first problem. We have a 450 nanometer light incident parallel with the bottom surface of an equilateral prism. We want to find the index or the angle of refraction at the first interface between the air and the block, which we're going to assume this is just glass, so it has an index of refraction of 1.5. And we are also going to find the angle of refraction as the light leaves this prism. Okay, so let's go ahead and get our tracing skills out here. Hopefully at home somewhere, because you guys don't have the luxury of having me in here to give you these, you have one of these fancy rulers at home somewhere, or at least a straight edge that you can use. So let's go ahead and solve for this first angle of refraction before we end up drawing all of this. So using Snell's law, n sine of theta equals n sine of theta. So we have 1.0 sine of theta. So this angle, so this is parallel with the bottom surface. This is 60, this is 60 degrees. So that means our angle of incident is 30 degrees. So we are going to say sine of 30 degrees equals 1.5 sine of theta. And that is the theta that we're going to be solving for. So when we plug that into our handy calculating device, we get theta refraction 1 is 19.5 degrees, which is good because we're going from a lower index of refraction to a higher, indicates that the light should bend towards the normal. So once again, you got to keep really good track of this. Remember, all the angles are off of the normal, so make sure you put your dashed line through here. So here is angle of incident, and we are going to be bending towards the normal at 19 degrees, okay? So this right here is our 19.5 degree angle. Okay, so that brings us to the second surface, and we're going to have to find the angle of refraction from here. So we want to draw another normal line perpendicular to that surface. Obviously, since we are now going from glass to air, the light should bend away from the normal since we're going from a higher to a lower index of refraction. If this angle gets steep enough, eventually, instead of having a refracted ray, everything will be internally reflected based off of this angle. Now, that brings us to our next problem. This is our new angle of incidence here. Okay, so we're going to have to walk through the triangle in order to get that value because it is not 19.5 degrees now. So if you remember from geometry, all these internal angles here have to add up to be 90, or add up to be 180, I'm sorry. So that means that this here, if this is 19.5, this is 70.5 degrees. And since this is 60 and this is 70.5 degrees, since it has to add up to equal 90, this angle here is, I'll put this out here, 49.5 degrees. And since that is 49.5 degrees, this is a 90-degree angle here, so that's going to give me a new angle of incident of 40.5 degrees. Okay, so that's why you're going to have to walk through this in order to determine that angle. So as we plug this back into Snell's law, 1.5 sine of 40.5 degrees equals 1.0 sine of theta. So theta refraction 2 is now going to be 76.9 degrees. And once again, as I mentioned in turning in assignments, since a lot of you are going to be doing this stuff on your own sheet of paper, please make sure you box in your actual answers, unless it's a written out explanation, but show your work, box in your answers so that I can see where those are located at. All right, so that tells me, obviously, since my incident angle was 40.5, that is good that we're bending away from the normal. So we're going to put this up here. What I usually do is put this straight with my incident, and then I just tilt it away from the normal so that we can sketch this arrow out as it leaves. This gets really tricky, and you're going to have to make sure you play around with this. You know, so one of the problems I think goes from a higher to a lower. So like it would be similar to having light travel through glass, and then you have a prism the shape of just empty container, just a triangle, and excuse me, and you insert that into the water. Well, now the angles are going to bend away from the normal on the first interface, but then back towards the normal on the second one. So it does get a little bit confusing. All right, we've seen this question before, so I just wanted to make sure we go back and review it. Let's find the wavelength of light inside the prism. Okay, so the incident light in the air was 450 nanometers. I just don't want us to forget about this. Remember, N is simply the ratio of the speed of light to the speed of light through the medium. So speed of light through the vacuum, ratio of the speed of light through the medium itself. Since C equals wavelength times frequency, remember what changes, and I will call this wavelength prime, what changes is the wavelength as the light goes into another medium. The frequency stays the same. So we can cancel that out. So N is simply a ratio also of the two wavelengths of the light as in the medium and versus in the vacuum. So we can now solve for this. 1.50 equals 450 nanometers over wavelength prime. And that's a pretty easy calculation there. So wavelength prime then is 300 nanometers through the glass block, or through the prism. Okay, that takes care of our first information video I will have posted on Canvas when handout 6.21 will be due.